All right, so the last class we had left off here talking about finding the limit of this particular function as x goes to 0. And I said you can't just directly plug in 0 because you can't have 0 in the denominator, right? Yes. You can't divide by 0. So what are we going to do here? We could check that way. We could take the tabular approach. That's not wrong. But there's another thing we could do so that we can solve this algebraically instead of having to use a table. We could say, what we want is first to get this square, the square root, out of our numerator. So we're going to multiply by 1. We're going to choose our 1 in a very particular way. We're going to say, hey, I remember from algebra that if I take a minus b and multiply it by a plus b, this thing is equal to a squared minus b squared. Okay. Well, in the same way that you have an a and a b here, and we square them, we're going to have an a and a b here that happen to get squared as well. What we're going to do is we're going to say let's imagine that a is equal to the square root of x plus 1. Okay? When we do that, that automatically gives us b has to be equal to 1. So now, when we multiply by 1 over here, what we're going to do is choose the conjugate form, right? We choose a plus b. We're going to multiply by 1 by saying this thing is like the square root of x plus 1, that quantity minus 1, all divided by x, times the conjugate of this numerator. Is it echoing really bad?
Yeah.
Hold on just a second. All right. And if somebody else with one of these laptops wants to open up Zoom and just monitor the chat so you can shout out if somebody tries to communicate, that would be awesome. But getting back to this problem, what we're going to do is choose our 1 to be represented by the square root of x plus 1, that quantity, plus 1 divided by itself. So that's just always going to be 1, right? It doesn't matter what happens. We're always going to have this canceling itself out. So now when we do this, we're going to have, according to this, the square root of x plus 1, that quantity squared, minus 1 squared, divided by x times the square root of x plus 1 plus 1. Right? Well, hey, this square and this square root are going to cancel each other out, aren't they? So what we're going to have then is this thing comes out to be quantity x plus 1 minus 1 divided by x times the quantity square root of x plus 1 plus 1. Now we've got a bunch of cancellations here. did it go? Oh, there. All right. So now we have a bunch of cancellations. In particular, these two ones are going to cancel when we drop the parentheses, right? So what we're going to do up with is x divided by the quantity, x times the quantity, square root of x, plus 1, plus 1. But hey, we have some more cancellations, yet again. Now, these x's are going to cancel out, right? So lo and behold, this thing is equal to 1 over the square root of x plus 1 whenever x is not equal to 0. And this, I can take and apply the limit to. The reason why we can apply the limit to this directly is because we're no longer going to be dividing by 0. So everybody remove this? So all we've done here is we've rewritten our original equation by multiplying by 1. We rewrote it in a way that lets us apply the limit directly. So these two forms are equal everywhere except when x is equal to 0. And the reason why is because we can't divide by 0 here, but x can be 0 down here. Everybody cool with that? So now, when we want to find the limit as x goes to 0 of square root of x plus 1 minus 1 all divided by x, this is going to be equal to the limit as x goes to 0 of the square root, my mistake, of 1 over square root of x plus 1 plus 1. X can be 0 here, so setting this to 0. This is going to come out to be 1 over square root of 0 plus 1 plus 1, or square root of 1 plus 1, or just 1 over 2. So what the hell did I just do? Because a lot of stuff just happened here, right? That's the next obvious question is like, how did we go from this thing to getting here, and how did we know we needed to do this process, right? So the way we know that we need to go ahead and rewrite this in the form of an equation we can actually solve is because we couldn't apply the limit directly. We couldn't say, let's just make x equal to 0. We couldn't do that because x is in the denominator, right? Can't divide by 0, so we can't just algebraically apply the limit straight away. Instead, what we're going to have to do is rewrite this thing in equivalent form for everywhere except where x is equal to 0. The easiest way to do that is to multiply by 1. And the way to recognize to do that is by recalling some algebra. Saying at the very least, there's a pretty obvious way of rewriting our numerator. So let's do that first. Let's test that first. That's all we're doing here, to say, I think if we multiply by 1, we can at least rewrite our numerator. Maybe something will shake out that way. After we do that, we find all of these cancellations occur. And all of a sudden we get a new form that when x is 0 will give us an answer. So this thing has to be equal to that everywhere except where x is equal to 0. Right? Now we can say, instead of writing out a table, let's just directly apply the limit. So the reason to do this is because the alternative would be to write out a table like this. To say, all right, when x is less than 0, what does our function approach? When x is greater than 0, what does our function approach? And this is computationally more work than the algebraic approach, right? Like, could you imagine having to check this value over and over and over again for smaller and smaller digits closer to 0? And even then, you're not guaranteed necessarily to get an answer, because we could have functions that do some crazy things where they oscillate very quickly between small groups of numbers, right? So what I mean to say is this tabular approach is great until you run into problems with functions like this. Where we bounce back and forth very quickly, close to 0. When we have problems like this, you're going to have to use tiny changes in x to write out a tabular form, a tabular solution. But even then, you're not guaranteed to find those right steps, right? Like, what if you start off with 0.9, then go to 0.99, then go to 0.9999. And that just happens to correspond with the peaks of this particular function. Then you're not going to get the right answer, right? You might be able to figure it out, reason it out, but you're not guaranteed. So the tabular approach is great in theory until you run into problems like this. And this is why we need these algebraic approaches, like what we just saw. So the rule of thumb in solving for limits is going to be avoid a table. You don't want to use this. They take too much time, too much work, and they may not necessarily give you the right answer. Instead, try to solve it algebraically to find an equation, a function that's equal to your original function everywhere except at a point. So what we're doing is we are hacking this replacement theorem. What replacement theorem says is that you have two functions that are equivalent everywhere except at a point. Then taking the limit as x approaches c of your first function is going to be equivalent to taking the limit as x approaches c of your other function. Does that make sense to everybody? In other words, we've got two functions here. F of x is equal to x plus 1 minus 1 over x. Then we have the function we just solved for, g of x, which is equal to 1 over square root of x plus 1 plus 1. And f of x is equal to g of x everywhere except for x equal to 0. So we didn't find the exact solution, right? That's why we had to have that catch there about x not being equal to 0. Let me get back to that problem. That's why we have to make this little addendum that x is not equal to 0. Because these things, They're not exactly equal. They're just equal everywhere except. So by replacement rule then, the limit here has to be equal to the limit here. Is everybody with me?
So we can ask for the answer, is the correct answer one that?
Yes.
Okay, so we have to solve that all of that.
Yes. Yes. Now, some slightly easier examples to see, to visualize. We've already talked about this example, but I think it's worth going over again. We got our function f of x is equal to x squared plus x minus 6 x plus 3. So here, x can't be -3. And the reason why is because when x is equal to -3 and 0, or denominator. So lo and behold, we get something that does not exist. But we could factor the numerator like that, right?
So then would the limit be +2? Or,
So what?
oh, it's still, well, because if you, that x plus 3 would cancel out, right? So then
Right.
you have x minus 2, which then x equals 2. So would that be a limit? Or what would that be?
Well, that's the point here is what happens is after we have that cancellation, we get x minus 2, right? But x minus 2 has an answer when you put -3, right? It doesn't be -5. So these two things have to be equal everywhere except where x is not equal to negative. Or I mean, except at x equals negative. So what I would say is so what we've got now is a g of x equal to x minus 2. And what all of this tells us is that f of x is equal to g of x whenever x is not equal to -2. This exists at -3. This does not exist at -3. And after going through all the simplification, all we're doing is saying, these things are the same, but this has an answer when x is equal to -3. Let's take that out. Does that make sense, what I mean?
So the final answer would be exactly, x minus 2.
Yeah, so now we'd say, all right, just did a whole bunch of work, but what we want to find is the limit as x approaches -3 of x squared plus x minus 6 divided by x plus 3. But by replacement theorem, we can swap out functions and say, that doesn't give me something I can work with very easily. So instead, let's find the limit as x approaches -3 of x minus 2.
So that would be your answer.
So now we can say, oh, no, the answer then is -5. So what's happening? What's happening is our original function has a hole right here at -3. we're plugging that hole with another function. Because we can plug that hole with another function, and that other function has a clear limit that we can evaluate. Let's go ahead and use that instead. That's all we do.
So basically, you have to denominator is equal to 0 when you fraction it out.
Whenever the denominator is going to be 0, you're going to have to do some massage. Whenever the function, more precisely, whenever the function is undefined at your limit, that's when you're going to have to apply something like this. There is, however, one catch to this rule, to this generalization. It may be the case where this has a hole here, but there's another point that's associated with it somewhere. So your function's not undefined there, it just has a discontinuity, a pointwise discontinuity. Everybody cool with that? So, all this is all well and good, but you really haven't talked yet about what these functions represent, what all is actually happening with the. Give me just a second here to open up an example. Business calc videos. Share. So need to stop sharing here. Yeah, code, lots of code. All right. So this is like jump this button. This is the other one. Beautiful, perfect. All right. So what our limit is doing. We need to exit out of the one. Oh, what the hell? There we go. Wait a minute, sure, I think it's in there. Okay. So, what is functionally happening here is a limit is saying mathematically, let's squeeze in the y-axis, but we can think of it as let's squeeze in the x-axis. When we get really close to our limit, x approaching a, we've got this value that we're saying we let it get smaller and smaller and smaller and smaller and smaller, so that when we subtract it from a, we start moving into a, right? So you're going to take a minus some values, let that value get really small, and you're going to move into it. Then you're saying, let's add it, so we're going to move in from the right. So we've got it moving in from the left and the right. And when that happens, what happens up here in our y-axis? Because that represents what's happening along our function. Does that make sense what I mean? So we're effectively saying, let's find a bunch of x values, move them in really close. Then let's take all those x values, throw them through our function, and look at what's happening in the y-axis. If both of those values approach the same value L, then we would say that the limit as x approaches a of our function is equal to L. But notice we could break this up into a left-hand limit and into a right-hand limit. So we can approach just from one side of the other. That's what we're going to be talking about next. But before we do, I want to give another example that I think will help explain a little bit. Sure. Okay. Now to help build some intuition, let's say we have a jump that's continuity like this. So a function that goes from one thing and jumps way up to another thing. Notice when we come in from the left, we approach L negative. But when we approach from the right, we approach L positive. Our limits don't agree. So in this way, we're saying we don't have a limit, but we do have sided limits. Coming from the left, our limit is L negative. Coming from the right, our limit is L positive. Is this visualization help a little bit? All right, come back over here. So what we just saw was the left-hand limit and the right-hand limit. This is the limit as we approach from the left, and this is the limit as we approach from the right. We represent it with a superscript to the right of whatever value we're approaching. And so let me write that up here. All right. So to represent whether our limit is a left-hand limit or a right-hand limit, we use these superscripts negative to represent the left-hand limit because we're coming from values less than it. And then positive to represent the right-hand limit because we're coming from values greater than it. Make sense? If these two limits agree, then we say the limit exists. So we say that the limit as x approaches c of our function is equal to L if and only if the limit from the left as x approaches c of f of x is equal to L, which is also equal to the limit as x approaches c from the right. This is math for if and only if. Which means if this is true, then this is true. If this is true, then that's true. So the two things imply each other, is what it's saying. And looking back, thinking back to that image, right, that GIF that I've just shown y'all, it kind of jives with the intuitive implications, right? What we were saying was, if as we approach, our y-axis also had that thing approaching, right? That's what this is. Then this exists. Does that make sense what I'm trying to say? Yeah, cool. So as an example of where the limit doesn't exist, but we do have these one-sided limits exist, let's imagine we've got f of x divided by, or f of x is equal to the absolute value of 2x divided by x. First, what do y'all think this comes out to be? So what? Well, the limit won't exist, but your one-sided limits will. So it's going to help to have some definitions here to make more sense of this. First, what does the absolute value actually mean? What is it?
If it's negative, it makes it positive. It makes it everything like positive.
Right.
No matter what.
So the absolute value of x is equal to x and negative x. Negative x, whenever x is less than 0, right? And x, whenever x is greater than or equal to 0.
Substitute.
Almost. You're on the right track. First, before we solve this, let's think about another analogous problem. What would x over x, the absolute value of x over x be? Well, go ahead.
That's probably the answer, the positive x instead of
Almost. So let's rewrite this as negative x divided by x, whenever x is less than 0, then x divided by x, whenever x is greater than or equal to 0.
Compound would be negative x.
X divided by x? -1, right?
Yeah.
So this thing's going to come out to be -1 and 1. So you'll have the right idea here. Okay. In that case, intuitively thinking about this and comparing to this, what is this going to be? 2 negative, right? Yeah, right. So looking at this thing, f of x equal to the absolute value of 2x over x is going to be equal to -2x divided by x whenever 2x is less than 0. And 2x divided by x whenever 2x is greater than or equal to 0. So this is going to come out to be -2 and 2. Whenever this actually reduces really nicely to whenever x is less than 0, and whenever x is greater than or equal to 0. So this graph is going to look like this. This is 2, this is -2. Because all we're doing, we're saying we've got a function that's constantly equal to 2 whenever x is greater than or equal to 0. It's constantly equal to -2 whenever x is less than 0. Everybody cool with this?
So why on the limits of just like less than on one side and certain is
Because when x is equal to 0, does it matter if we have plus or minus? So depending upon the way you want to really define this, this could be a point that doesn't exist, or it could be a point. This is kind of up to interpretation at that point. But the reason why is because at 0, plus and minus doesn't really make any difference. It's just 0. The other catch here is we are dividing by x, so this technically should not exist.
I already drew it.
This is one of those like technicalities that I would not call y'all on. So looking at this, our limit definitely does not exist, right? Because the limit from the left is going to graphically be -2. The limit from the right, graphically you can see is going to be 2. We've also shown that algebraically as well. Everybody agree with this?
Why is it not x is greater than
It's a technicality because we're dividing by x. So it can't be 0. That's why. And I didn't catch that when I first wrote it up here. That's one of those really easy, simple mistakes to make. Especially when you start from the definition of an absolute value. Right? Just want to keep that equal to sign of it. But like I said, we've got our limit from the right. As x approaches 0 from the right of the absolute value of 2x over x, this thing's going to be 2. The absolute value of the limit as x approaches 0 to the right, 2x, the absolute value divided by x, is going to be equal to -2. So here, we would say, like I said before, the limit does not exist. But we would say the right-hand limit is 2, and the left-hand limit is -2. Everybody cool with this? These sorts of jump discontinuities, you're typically only going to see them in piecewise equations. Typically, it's when y'all are going to see them. So whenever you see an absolute value or a piecewise equation, go ahead and check things, drag them out if you can, and verify what you think is happening, what you found is happening, and check your work that way. Cool. So something to be aware of, piecewise functions, be mindful of how limits behave. So again, the limit of the left and two to the limit of the right. And one more time, the limit as x approaches c of our function is equal to L if and only if the left-hand limit and the right-hand limits are also equal to L. So another piecewise equation. Looking at this, what's your intuition tell you? First, does the limit exist? What happens when you plug in one? What happens when you plug in one? Also, right? So presumably these functions are going to have a limit. Because even though they're broken up, below x is equal to 1 and above x is equal to 1, at 1, they both are equal to the same thing. Presumably, we might have a limit here. And the way to check is to say, all right, well, the limit as x approaches 1 from the right, well, here we can just plug in 1. It is in fact 3. Here, the limit as x approaches 1 from the right, just plug in 1 again. On the whole, could that be 3? So, conclude from that the limit as x approaches 1 of our function is 3. Even though our function doesn't exist at 1, we didn't define it there, right? We left out 1. We can still say it has a limit at 1. So this thing has a hole right here. And we're able to plug it with our limit by comparing what happens from the left and what happens from the right.
Did you just pick one randomly?
Could I?
Wait, like, is that what happened? Like, how did you select one?
Because it approaches one, is that why you use
Is
one?
that why?
Yeah, that and so the thing I was looking at here was x approaches 1
Okay,
and our discontinuity is
it's
at
right
1.
there, one. So is that what we'll typically look at, is we'll want to look at?
Yes.
Right there?
And that's usually what the limit's there for, is to plug these holes.
Yeah.
If our function's not defined at 1, like it is here, right? You have nothing at 1. You define below and above, but not at.
We don't have the equal to sign.
Right. What happens in that case? This shows up a lot in things like physics, where it might be easier to define what happens on one part of time, what happens in another part of time. But we don't know if our solution exists everywhere because we have this discontinuity. So we need to use the limit to plug those holes.
So if it was greater than or equal to, we could plug
If it was greater than or equal to, you would still have to check because what if this approaches 4 and this approaches 3? Makes sense what I mean?
Yeah.
So what if instead we had yeah, this takes a long time to erase. What if we instead had the function g of x is equal to 4 minus x, x is less than 1, and 4x squared minus x, instead 4x minus x minus 1, x is greater than or equal to 1. All I did was subtract 1 here. So now we're gonna go to 2. 2 from the right, 3 from the left. So now our graph would look something like this. We had that huge jump, right? You still have to check it just in case.
So we're gonna check what's at the other end of the greater.
Generally, what you're gonna look for is, all right, what is X approaching, right? That's where you're gonna wanna check it. If it happens to be the case where your function is broken up in a piecewise equation around that point, check it there. We could, however, have said, find the limit as X approaches, I don't know, 2. So then we would only need to check what happened on the side here. Well, this is a continuous equation. So we can just plug it right in there. Does that make sense what I mean? So we're piecing things together. We're saying X is approaching 1, we're broken up at 1. So all we really need to do is throw in 1, double check it. We could have also have easily said something like 1 over X minus 1. Which would cause us more headaches, right?
Yeah.
Because this is discontinuous in and of itself at 1. What happens? So there's, right, so my point here is that when solving these problems, be mindful of what the equation and the problem is asking, right? The equation here is telling us we break up at 1, do something below 1, do something above 1. Well, the problem's asking is what happens at 1 if this thing was continuous. Another example, piecewise functions like this are usually, like I said, when you're going to see these discontinuities show up. Here is going to be a great example of that. Here we've got a function. It's going to look something like this. Well, 14, 16, right? And here, here, here. 1, 2, and 3. So we want to show that the function doesn't exist, or I mean that the limit does not exist as X approaches 2. Why is that? Well, what we've got is as you approach 2 from the left of our function, as we approach 2 from the left, we're going to get 14 out, right? Now, coming from the right, this is going to be equal to 16. So the limit does not exist. It doesn't exist because we don't agree on what we go to from the left and from the right. You know, with that picture with those jets were showing us, right? Coming in, what happens over here? Well, we just stay here. And we just stay here. We never agree on an answer. So it doesn't make sense to say we have a limit, but it does make sense to say we have a limit from the left, not a limit from the right. Folks at home, are we cool with that? I'm gonna assume that is, oh, sweet, it does let me pull up the chat. Cool, awesome. All right, so looking at this problem, again, breaks out like a step function. The limit from the left is 14. The limit from the right is 16. Equal to 3. So the limit does not exist.
So how would you determine it? Just by graphing it?
Say what?
Would you have to graph it to determine that?
Yeah, so like if that question was asked, how are we supposed to answer it on the home?
Well, we can look at this problem and say, coming from the left, we're in this interval, right? From 1 to 2. Coming from the right, we're in this interval, 2 to 3. In this interval, we're just equal to a constant value. So the limit has to be that constant value from the left. In this interval, we're a constant value. So the limit from the right has to be equal to this constant value. So we can just say directly that the limit from the left is 14, the limit from the right is 16. Just like what I wrote up here. I'm just showing this graphically to help verify what the math is telling us compared to what we can see into it just from the graphs alone. So just like what we've got up here, this just happens to be because of the way the intervals are broken out, right? They're just constant functions of these intervals. So what about a case like this? We want to find the limit of 3 divided by x minus 2. Does the limit exist? This function is going to look something like this. What do we think? What's the limit here? Well, coming at it from the left, we go down forever, right? Negative infinity. Coming at it from the right, we go up forever to infinity. So the limit from the right, as x approaches 2 from the right, of 3 over x minus 2. This thing's going to be equal to infinity. And over here, the limit as x approaches 2 from the left of 3 over x minus 2, things equal to negative infinity.
But it would never touch 2, right?
Right, our function would never actually touch the line x is equal to 2. So this is another example of a jump discontinuity. This is actually an asymptote, is what this line is called. So here, the limit doesn't exist because coming at it from the left, we go to negative infinity. Coming at it from the right, we go to infinity. So we go to the furthest 2 points you could ever get to, right? So they are as far apart as possible. So it must be the case that the limit does not exist. Make sense what I mean? I should have put a Mean Girls GIF in here. The limit does not exist, except what this problem is. So pro tip here, graphing things, it's going to help you a lot. It's going to let you see some things and just intuit what you need to do. Especially with limits.
I mean, if the test is online, you won't even know.
Well, now I know. My thing about graphing calculators, if you can run a spaceship with it, no. But if all you can do is get pretty pictures, then go for it. Make sense what I mean? And the reason why is because there are some problems that graphing calculators can solve now that this class is going to ask us about. And I want to avoid that particular hiccup. Cool. So that was the end of that section. We're an hour in, and I'm going to let everybody take a 10-minute break. So what?
I said a warm-up break.
A warm-up break, yes. Wait, what? It's already hot enough, a cool-down break.
No way. It'd be cold.
Fake news.
I didn't say.
Wrong.
I think it's warm in here too.
I think the fan's blowing.